Okay, so last time we learned that loudspeakers do not send sound in every direction equally. And that's on purpose. Okay, there are actually not very many loudspeakers that humans make that actually go equally in all directions. They do exist. There are some that do that, but very few, and they're used for very specific things. But most of them, we try to get that energy to go one way. Anybody remember why? What are the reasons why? What are the benefits we get by confining that sound in one direction?
Makes it louder.
Big part of it makes it louder, right? And making it louder is a big part of what we do. So, yes. Any other things? Yes, Kai?
You can make it go more places. Like, direct it to different places.
Yeah, because like we want it to be where the ears are. And we want it to not be where the ears are not. All right? Because you start putting the sound where the ears are not, and that can create new problems, like reflections that can create comb filtering, that can create frequency response problems, that can, all of those things that we've already talked about. So we also learned how the different ways that we document that loudspeaker directivity. And here's an example of a loudspeaker. This is a polar plot. Well, it's got a bunch of different graphs. So this is something from Electro Voice. Now I want to show you just a couple things about this. First of all, if you look at the spec sheet for this thing, it says it is a 60-degree horizontal by 60-degree vertical loudspeaker. Now, given what we learned last week, is there anything about that might give you reason to question? Yes, Jaden.
So, based on what we learned last week in directivity, I'm assuming it starts losing dB at 60 degrees vertical and 60 degrees horizontal.
Yeah, so that means that at 60, there's a 60-degree angle between the 6 dB down points. So you go 30 degrees on either side in any direction, and you're basically 6 dB quieter. But here's the thing that gives me pause about this and gives me cause to question. We know, because we learned about it last week, that it's actually not possible that that's happening at every frequency. Not possible. Okay? There are a lot of really smart people that are trying really hard to find a way to make that possible and coming astonishingly close. I mean, some of the stuff that's coming out right now, D&B just came out with this big line array that's like vented on all sides and everything, and they're getting pattern control out of one cabinet down to like 150 hertz or something. And that's pretty awesome. So I don't know, maybe we're finding this thing that we used to think was impossible, and now we're starting to find ways to do it. But it's still, I think, technically not possible that this is happening at every frequency. So what does it actually mean then? Well, we can sort of start to see, right? If you look at the beam width plot, it's sort of doing that 60 by 60 thing in this area. But it's not doing it down here, right? We can also see that, in this one, there's that 30 degrees. That's the 6 dB down point, right? And the other thing that happens when you hit that 6 dB down point is the frequency response starts changing more than we would like. You can see generally, as you're heading towards the 30 degrees off, the high frequencies are going to get quieter, but they're mostly getting quieter with some amount of consistency. Once you get to 30 degrees, it's starting to get inconsistent in the way that it's attenuating those frequencies. And that's why we start carrying. It's one of the reasons why we start carrying once you cross that 6 dB down point. Because after that 6 dB down point, the frequency response has now become irregular enough that we're sort of not comfortable with that. So that's the good news, is so far this loudspeaker is behaving the way you would expect. Here are the polar plots. Now, what they're trying to do is, in order to not make this a 30-page spec sheet, they have superimposed several polar plots on top of each other, and they're doing dashed lines and colors to plot different frequencies. So you've got vertical and you've got horizontal, all the way from 200 hertz to, what's the high? It'll go all the way up to 16 kilohertz. So you can see, like, it gets narrower and narrower, like you would expect. Generally speaking, we think about that 60 by 60 thing, whatever they say in the spec sheet. Rule of thumb is that's probably 1 kilohertz. But the manufacturers have been known to take some liberties with that. They've been known to find a different frequency that tells that story a little bit better, and they'll use that as the thing. So you have to go look. All right, so this is the loudspeaker we're going to use. This is a section view of the Stevens Center. So what I want to do is I want to take you through the process of figuring out, if this was the loudspeaker we had to use, how do we get it to distribute the sound across the area where all the ears are, okay? For purposes of our discussion today, we are going to pretend the balcony doesn't exist, or at least that we can't use it, which is actually real right now. We can't actually use it. So it's fine. No balcony. All we're worrying about is the lower level, the orchestra area, okay? Now, we are also going to, just for purposes of making things simpler, we are going to presume that the only place we can hang is right here. Okay? There's some holes in the eyebrow that allow you to hang a truss right there. Okay? So we're going to assume that if we're going to bring this thing in and hang it, that's where we get to hang it, because that's where the truss ends up. Okay? They're not going to cut new holes in that eyebrow just because we want to put it somewhere else. Okay? The only people that get to do that is Phantom of the Opera. Do you know about the Phantom holes? So every touring house in the country that's ever had Phantom of the Opera has holes punched in their ceiling at the very specific spot for the Phantom of the Opera rigging system. They're called the Phantom points. And so a lot of touring productions kind of design their touring rig around the Phantom points, because most of these theaters have these things where Phantom of the Opera came through sometime in the last 30 years and poked these holes in their ceiling to access their roof steel. So Phantom of the Opera has never played in Stevens Center, so we don't have Phantom points. We could make some, but we do have a couple holes in the eyebrow that we can hang a truss off of. So this is where we're going to put it. Now let's just, for purposes of discussion, let's start by defining where is the sound going to have to go. Well, we have a front row, right? So I'm going to assume this is the back of the front row, so I'm just going to draw a little line up here at 4 feet, which is approximately where the ears are going to be, ish. Maybe, obviously people's torsos are different lengths and things, but generally speaking, I think 4 feet is a safe. It's a little bit high. I think it's, most people say it's more like 3.5 or 3.25 feet, but we'll say 4 just because it's an even number. That's where the ears are going to be. So I'm going to draw a little point there at the front row, and I'm going to draw a little point here at the back row. Back row will be, we'll say it's there. And then to give myself a little reference, I'm going to do one in the middle, which I'm going to say is there. That look like middle to you? Looks like middle to me. Okay. So we have front, middle, back. Now, we have something that the manufacturer says will distribute the sound relatively consistently within a 60-degree angle. Well, if I was new to the sound game, the first thing I would probably think of to do is see, well, what is the angle between the front row and the back row here, right? What are we dealing with? What are we dealing with there? What is that angle? Be nice to know. I hope it's 60. Right? Let's see. We want angle. It is 48. Okay, so you might be thinking, great, we're in business. I got a 60-degree loudspeaker, trying to cover a 48-degree area. Good to go. This loudspeaker they told me I had to use, I will be all set. Well, let's see. Okay. I'm going to draw a third line here to here. Now, I'm going to open up a little spreadsheet because we're about to remember a whole lot of numbers. Okay. So I'm gonna put Excel to work for me. And I'm going to have a, let's see, front row, middle row, back row. Okay, first thing I want to know in order to figure this out is how far away are all these seats? Because we know that the farther you get away from the loudspeaker, the quieter it will be. We learned that a couple weeks ago. So there will be, if our goal is to deliver the sound equally to all these seats, we need to first think about what role is distance playing in this. Because some of these seats might be closer, and some of these seats might be farther, and that will affect how loud the sound will be. Right? So let's see what we're dealing with there. So the first thing I will do is just measure each of these seats. So from the loudspeaker to the front row, 33 feet 2 1/4 inches. So I'm going to call that 33.2 1/4 would be, I'm going to say 0.15. I don't want to do that math. Close counts in sound, okay? An extra couple inches is not going to make or break this equation, okay? So that's front row. Middle row is 50 feet 2 inches. So that'll be, I'll do 50.1. Back row is 79 feet 9 5/8 inches. So I'm going to call that 76.75-ish. Okay? That's the distance. Yeah? Okay. So if we point this thing, again, if this is my first, if I'm new to this, my instinct is probably going to be to aim this at the middle seat and hope that that 60-degree angle works in my favor. Okay? So that means that from a directivity point of view, if I care about directivity, that middle seat will be my on-axis point. That's 0. 0 degrees, right? 0 degrees, 0 dB. So that's 0. That should be whatever the loudspeaker does. And what I want to do now is figure out what will be different when I go to those other seats. Okay? So I'm going to call this off-axis, this row. I'll make that a little bit bigger. Okay? All right. So dB loss distance. So now I want to ask myself, what is the dB loss over distance here? Well, at the front row, all I need to do is figure out what's the decibel difference between these two distances. Okay? So what would be 20 times the log of 33.15 divided by 50.1? Somebody do that. 3 people do that. It's not right until 3 people get the same answer. 20 times the log of 33.15 divided by 50.1. Negative 3.5 what? 9. Anybody else get that? Yeah. Jesse got that? I need one more person or it's not right. Anybody else get 3.59? Negative 3.59? What? Robin got it? Okay, great. Must be right if 3 people got the same answer. Okay. We're assuming 0 degrees dB loss over distance for the middle row because that's where the loudspeaker's pointed. We know, of course, we will lose some going through the air. We're just saying that from the point of view of comparison, the starting point is the on-axis point. Okay. Okay, what about the back row? 20 times the log of 50, well, let's see. 20 times the log of, did I do that right? This would actually be positive. I should have done 50.1 divided by 30. So this will be louder at the front row because the front row is closer to the loudspeaker, right? So what we want for the back row is 20 times the log of 50.1 divided by 76.75. That'll get us a negative number. The back row is definitely farther away, so we should get a negative for that. 20 times the log 50.1 divided by 76.75. Negative 3.7. We have 3 witnesses on that? Okay, good. All right. Excellent. So right out of the gate, assuming this is an omnidirectional loudspeaker, we have approximately a 6 dB range between front row to back row. That's acceptable. 6 dB is sort of what we think is anything more than that, and we would say is not acceptable, right? We'd love it to be less than that if we could get it, but acceptable. Well, let's start talking about the directivity loss now. Now, just for purposes of conversation today, we're just going to look at 1 kilohertz, okay? But in real life, you would look at, you know, I would suggest 500 hertz, 1 kilohertz, 2 kilohertz, 4 kilohertz. Look at those 4 octave ranges, and if you can make it work for those 4, it's probably working everywhere else, okay? 500 hertz, 1 kilohertz, 2 kilohertz, 4 kilohertz. Those are just octave bands, right? I'm doubling every time, right? So what is the angle? Well, 0 is middle row because that's where we've pointed it. But what is the angle off axis to the front row? Well, I just measure this. 33 degrees. 33 degrees. What about to the back row? 15 degrees. And then I'm going to make a cell here that says directivity loss. Presumably it's 0 at the middle row because that's where I've pointed the loudspeaker. That's on axis. And I want to know now, how much do I lose going 33 degrees down off axis and 15 degrees up off axis? So let's go look at our polar plot now. So 33 degrees down, 1 kilohertz is the orange line. So here we go. This is the vertical. 0 degrees is the theoretical 0. And 33 degrees would be about here. So how much have I lost? Well, does it say how many dB per division here? 6 dB per division. Graph lines are 6 dB. So that would mean that
That's a horizontal one, right?
this is vertical. So this would be 6 dB, right? And we are looking at 33, which is actually about there-ish. So we haven't quite gone 6 at 1K. What would you say that is? If this is 0 and this is minus 6, what would that be?
4 or 5.
I'll say 4. It's not directly in the middle, so it's probably a little more than 3. So I'll say 4. We'll say minus 4. How about that? I better clear that before it freaks out on me. All right. We lose 4 dB going off axis to the front row. What about 15 dB up? Or 15 degrees up? Oops. There goes my mic. Sorry, YouTube. Okay. 15 degrees would be about here. Look at that. We got that really interesting drop there. What's that about? Well, this is an artifact. You get this on every single loudspeaker that has a low circular driver on the bottom and a horn on the top. When you go off axis the direction of the horn, you always get that little dip right in that 1K range. And the reason is because that's usually around where the crossover happens between the two loudspeakers, and you get a cancellation. Interesting enough, it doesn't happen when you go off axis the direction of the low driver, presumably because the level difference has become different enough between that horn and that on that axis, but it doesn't up here because of the pattern control of the horn. But you always get that. And no one has been able to figure out how to not get that in that configuration where you got low driver, horn on top. The only way they've figured out to get away with it is to load it coaxially and put the low driver behind the horn and the compression driver in front of that. And then you can get rid of that. But so for purposes of plotting directivity, you know that's an artifact that happens at a specific frequency because of the crossover of this loudspeaker. So if you're trying to consider full spectrum, is this going to work? You can safely ignore that for purposes of making a decision. It's not like you're going to not use this loudspeaker because there's one frequency that goes at that one particular angle in that one particular spot. Because full spectrum, it's not going to do that. Okay? So we can safely just sort of assume that's not there. Which means 15 degrees, interestingly enough, looks to be, I think I might have, it's probably closer to here, isn't it, actually? Well, it's probably about there. Probably 5 dB, isn't it? Maybe -5. All right, so what's our total? Well, what is positive 3.5 plus a negative 4? Yeah, so we're minus 1.5 dB at the front row. What about the back row? Minus 8.7. Well, shoot. Did I make a mistake?
Well, I'm just confused as to, yes, that number is positive for dB loss distance, but never mind.
Go ahead.
I just don't understand, like, that's still like a loss. Yet
I labeled it loss, but it should be saying like decibel difference because of directivity, right? So that's just me typing the wrong word there.
Okay.
But we got louder because we got closer, right? So the sum of the fact we got louder because we got closer, but then we got quieter because we went off axis, the net result is a minus 1.5 as compared to the middle row. Yeah, Dylan?
That should be -1.4, or -0.4, sorry.
Say what? Did I do this wrong?
There should be a 1.
Ah.
Unless I'm vastly screwing up on that.
Should I get my calculator out and let's just prove it?
I just mapped it. I calculated that math.
Dylan's right? Okay, good. All right. You got to catch me on my math. You know that. Okay. Well, shoot. We've got now what used to be acceptable is now not acceptable, right? We now have more than 8 dB difference between front row and back row, which is not ideally what we want. Okay. Well, it's a good thing this isn't my first time ever doing this, because I'm about to tell you a very important pro tip. if you want to instantly prove yourself as somebody who has some experience in pointing loudspeakers, this is what it is. Professionals usually point their loudspeakers at the back row. Okay? And inexperienced people usually point their loudspeakers at the middle row. Okay? So that's one of the indicators. If you want to know if you're working with somebody who has maybe, possibly an inkling of what they're doing, are they pointing the loudspeakers towards the back, or are they pointing them towards the middle? If they're pointing them towards the back, they've probably been down this road a few times before. Okay? With obviously some exceptions, but generally speaking, professionals point it towards the back. Why? Why would you point it towards the back? Well, let's see. I'm going to delete all of this because none of it matters anymore, because we're going to do something different. So we are going to now assume that we're pointing towards the back row, which means 0 degrees off axis, 0 dB loss over distance at that 0 degrees angle. We're pointing at the back row. Okay? Well, let's see here. How many degrees off axis are we at the middle row compared to the back row? Angle. $15 degrees, same as it was before. Now, what about back row to front row? 48 degrees. Oh boy, now we're getting somewhere. Okay, loss over distance. Let's compare middle row to back row. So this would be 20 times the log of 76.75 divided by 50.1. This will tell us, I'm going to change loss to difference, or change. Say it again. 3.7? Okay, good. 3 people got that. All right. What about front row? 20 times the log of 76.75 divided by 33.15.
7.29.
Kai says 7.29. Okay. That is the same thing. You would not hear a dB difference of 0.19. All right, cool. Well, I've done this twice here. I guess I don't need that cell, do I? Okay. Directivity loss. Well, presumably it's 0 at the back row. Directivity loss to the middle row, where we're looking at 15 degrees. So 15 degrees is here. And about there. We've maybe lost 1 dB, if we've lost anything, right? At 1K. So I'm going to say -1. Now, what about 48 degrees? Well, 48 degrees is going to be 30, 40, 50, 60. So 48. Wait, did I do that right? 30, 40, 50. 48 is going to be about here. It's right around 6 dB, isn't it? -6. 1K. I'm looking at the orange one. Okay, so what's the net result here now? Back row is 0. Middle row is 2.7, right? Back row is 1.29. I'm going to get paid for this job. I have less than a 3 dB difference between front row to back row. And all I had to do was tip that loudspeaker up and aim it at the back row. Okay, what just happened? How did that work? Why do professionals point their loudspeakers towards the back row? Well, because we are merging two principles here that we have now learned on 2 separate days. But if you consider them both at the same time, you'll understand what's happening. First principle is inverse square law. Sound gets quieter when you move farther away, and it gets louder when you get closer, right? First principle. Second principle is, with loudspeakers, sound gets quieter the further off axis you go. So here's what's happening. By aiming at the back row, that's our comparison point. As we get closer to the front row, we are getting closer to the loudspeaker, and therefore the loudspeaker is getting louder, but we are also going off axis, and therefore the loudspeaker is getting quieter. So we are both getting louder and quieter at the same time, which means it balances out. And as long as we are within that 60-degree angle that the manufacturer specified, we know that we are going to have relatively uniform frequency response. So here is the real question. This is where this falls a little bit apart for this particular loudspeaker, is we are 48 degrees off axis by the time we hit the front row, which is just outside that 30-degree window where we would, we're about 18 degrees out of that 30-degree window that we would have, because it's 30 degrees on either side. So the front row is maybe going to have a little bit extra high frequency loss, more than we would ideally want. But, a couple front fills could solve that problem if we had to. Get that extra high frequency in there. But generally speaking, we have achieved less than a 3 dB difference between front row to back row with one loudspeaker. We just had to point it at the back row. All right, everybody follow that? Yeah, Dylan?
I just wanted to check the reasons, like it was inverse square law, and if I was going off axis, they get, did you say louder or quieter?
Gets quieter when you go off axis, right?
I just want to make sure I read it.
So sound gets louder when you get closer to it. Loudspeakers get louder as you get closer to them, but they get quieter as you move off axis of them. Yeah.
Can you go over how you read the public file?
Yeah.
To get the directivity loss.
Yeah.
Like, how did you get it negative 60 dB, negative 1, fine?
Sure. So we know that, because it said so at the bottom of the page, that each of these lines represents a 6 dB difference in level, which means right here this is -6, this is -12, this is -18, so on and so forth, okay? So we know we're looking at this orange dashed line, because if I know that because I said we're talking about 1 kilohertz, and there's a key here that says 1 kilohertz is the orange dashed line. So, oh boy, ink didn't move. Okay. So this is 0 degrees. I know that because it says, sometimes now on the horizontal, the 0 degrees will be up here. But you just look for where 0 is. And then if we're looking for 30 degrees down, so this is the loudspeaker here. Right, we're looking at it from the side.
Oh, that's fine. It's from the side.
Right? Because that's where 0 is. Okay. So we're looking, 30 degrees, and it's halfway between 0 dB and -6. So that's probably -3.
Mm-hmm.
Make sense?
Makes sense.
Okay.
I guess I forgot that was vertical pine, and the speaker facing that way.
Yeah, this one, they don't always do that. Some manufacturers will have the vertical with plots with 0 on the top, but this one doesn't. Because if you look over here at the horizontal, 0 degrees is on top. So now you're looking at the loudspeaker, you're looking down on it, and it's here doing this, right? All right. Other questions? Yes, Courtney.
So kind of like when you're deciding what equipment to use, how this is a 60-degree loudspeaker, but the back row that we're directing it to is 48 degrees, would you, if you had the resources, get a different loudspeaker for that situation? Or?
Yeah, so assuming I had some flexibility here and I could go get something else, I know that if I aim it at the back row, that I'm dealing with a 48 degree, I would just round that up to 50 difference between back row to front row, which means if in a perfect world, I would be looking for a loudspeaker that had a vertical coverage of 100 degrees between 6 dB down points, right? Because it's 50 degrees to either side. So if I could find something that was 100 degrees vertical, I'd be golden, right? And I could do it with one loudspeaker. And those exist. 100-degree horns totally exist. You don't find them as often, but they exist. We have some. 90 degrees are more common than 100. But you do see the hundreds every once in a while.
Would that be twice the size of this loudspeaker?
I don't follow.
Does that make, because you said you could have 50 degrees and 50 degrees. Oh, is this loudspeaker 60 and 60?
Yeah, so it's 60 degrees horizontal, 60 degrees vertical, that horn,
okay.
right?
So you're talking about a 50 to 50.
Yeah, I'm saying like if what I'm talking about is I would want one that would be 100 by 100. Because when you say it's 60 degrees, that means it's a 60-degree angle between the 6 dB down points, which means it's 30 degrees to either side from that 0 on axis point. So if I want 50 degrees over here, then I'm looking for something that is 100 degrees between 6 dB down points. That make sense now? Okay. Anybody else? Jesse?
I know in passing strange we're using a line array for our front
Yeah.
main, and that the angle is much steeper than the example that you just showed
Mm-hmm.
from the speaker down to the audience.
Mm-hmm.
And not all of the individual speakers in the array are pointed at the back row.
Yeah.
So what is the difference in like calculation for that?
So line array is a pretty different beast. It follows slightly different rules. And I don't know that we've got the time today to get into that. For purposes of the homework you have to do, you're going to do things with a point source element. But a line array behaves quite a bit differently. Suffice it to say, there's different rules of thumb for that. Yes, Molly?
Doesn't that mean you have like a million different access points, and then do you calculate it like individually, or do you calculate it in like the whole?
It's even worse than that. We can talk about line arrays maybe in a couple of days. Once we get the concept of point source locked in our head, then we can get into what the line array does. But it does something very different. Okay. Yes, Courtney.
So I know when we're going to be working in Student Center, a lot of that system is already like a rep system.
Yeah.
When do you decide to use that rep system and when to bring in your own things?
Well, I am facing that conundrum right now. I'm about to go in and do ragtime in there, right? You're doing that with me. And I know we have like a day to load that system in.
Yeah.
So could I, an experienced sound designer with a certain amount of expertise, come up with a better solution for a center cluster than what is hung right there? Certainly. But is it worth the money, the time, and the labor to try to replace the center cluster, given the fact that I have a whole system that load in a day? Probably not.
Yeah.
I'm just going to use it there, and it's fine actually. In fact, I worked with D&B to design that center cluster in Stevens Center. It's fine, actually. It's a little high for my taste, but it's fine, right? So I think it's that calculus. Now, in your case, as students, you're going to go on a show. You know, we let you treat it as though it's an empty room. If there's something there and you want to use it, great. But if it's not, you don't have to. You can bring your own thing in, and it's not like it costs you money to hang something different. It costs you time. Your time doesn't necessarily cost money because you're not paying your crew as students. So that calculus is a little bit different for you. But one of the things I will do is kind of help you wrap your head around that, and I do that all the time. You see me do it on the looks all the time. It's like, cut that, cut this, cut that. You don't have time for that. You know, nice idea. But no, right? Is I try to help you with, because when you're starting out, you have a hard time wrapping your head around the enormity of what you've just decided to do, right? So, and that's one of my jobs as a teacher, is to help you skip over the last 20 years of my life learning to do it the wrong way. I'm going to help you skip over that and get to the stuff that I already know, which is like, don't do that. You get to choose whether you want to skip over that 20 years or not. If you would prefer to go through that yourself, fine. But if you want to skip over it, I can show you, I can help you skip over that, right? Okay, so we've got enough time. So now we got to look at the horizontal axis of this thing, and then you'll be ready to do the homework, okay? So let's take a look at another theater.
Can you just look at vertical axis for that?
What's that?
We only did vertical axis.
That's right. We only did vertical because we're only looking at the section view. But now I want to make this a little more complicated. And now we're going to go to the mill theater. I keep stepping on this. Sorry, YouTube. Let me see if I can.
Think about like have volume warning.
I'm going to just dress this cable a little bit. How about that?
Is that the mic for the camera?
It goes into here, but yeah. Okay. So this is DeMille. Maybe you've done a show there. Maybe you haven't. It's over there in Dance Land. It's an interesting little proscenium theater. Small-ish. What's interesting about it is it's like the seating area is this kind of bowl. It's this kind of curved bowl shape, which is really kind of annoying. But depth-wise, if you look at section, there's not very many rows here, but it just goes really wide. Okay, so anybody ever done a show in DeMille? A couple of you. Okay, what's hanging in DeMille? We've got a center cluster hanging in there that most of the time you guys use. Sometimes people hang something different, but what do we have hung in there? Anybody know? You don't know. It's a KF 300 from EAW.
Oh, yeah. You don't know. There sure is something
Okay.
there. Actually, it's not 300.
If you knew, I was going to be like, congratulations, but you don't know, so I'll just tell you. It's KF 300. Looks like this from EAW. There's actually two of them, and there's two of them, and they're straddling a sub in the middle, an EAW SB 330 subwoofer in the middle. The subwoofer, there's nothing particularly special about that subwoofer, other than, it's just a couple of big drivers in it. But the one special thing about that subwoofer is they angled the cabinet of that subwoofer so that if you slap two KF300s to the side of it, they are perfectly splayed horizontally. So the 6 dB down points overlap directly in front of the sub. And so you can actually, when you buy this, it's a package deal. The EAW, I don't know if they still sell this or not, but they will sell you a bracket. See if I can find that bracket. Here it is. They sell you this little fly bar, and the sub attaches here, and then so you would have the sub ends up here, and then the little KF300 ends up there, and KF300 ends up there. Okay, one pointed that direction, one pointed that direction. And then what happens is this spot here, this is where the 6 dB down points hit at a certain given distance. They're assuming something about the distance here, but whatever the splay angle or whatever the coverage horizontally of these things are, right, it's -6, which of course we know sums, when you take two -6 dB sources and you sum them together perfectly in phase, what happens? Zero, right? That becomes 0. So now you got 0 dB here, 0 dB here, and 0 dB here. And whoa, you've just created a loudspeaker that's twice as wide. Okay? Pretty cool trick, right? So I'm going to show you how to plot one side of that. But that's the trick, right? If you turns out that horizontally you're not quite hitting everything, and assuming that you've got some kind of directivity horn on this thing that has any kind of pattern control whatsoever, you can slap another one onto the side of it. Now you just have to splay them apart wide enough so that the 6 dB down points hit at the same spot in the room. And if they do, then they sum together back to 0, and now you effectively created a wider single point source. All right, so how did we do it? Well, I can tell you that that little center cluster is about here-ish. Oh, point styles. There we go. Do I have a layer already here or not? I don't. All right, let me make a layer. We'll do the red again since that's what we were doing. This will go to. All right. So that's about where it sits. And I'm going to try to plot that in the same spot on the section view, which is about here. So we are hanging it about there. Okay, that's about where that KF300 hangs. Close counts, in sound. So let's start mapping this out here. So we know that the front row will be, let's assume this is a dance show and the pit is covered. So if the pit is covered, then this would be the front row. Okay? I'll make my points bigger. Oops. Make them really big. Thought I made them big. 24 inches. There we go. Okay, so I'll put a point there. I will put a point here. And I will put a point there. And let me just plot those down onto the ground plan view. Okay, so ground plan view would be there and there and there. Now, for purposes of making things a little simple, I'm going to do a label here. This will be A. And then I'll just copy this. If you see me do anything in CAD that you're like, wait, how did you do that? Just stop me.
Can you go back and watch the recordings from the camera?
What's that?
Are you able to go back and rewatch the recordings from camera?
Yeah, should be able to.
I've never done that on Canvas, so I didn't know.
It's also on YouTube. So, all right, we're going to call this seat A, B, oops, B, and C. Oops. There we go. And down here, just so I can keep track of things, we'll do A, B, and C. Okay. So let's go to, this will be A, this will be B, this will be C. All right, so let's figure out our distance. Now we're going to have, let's figure out our distance. So distance from loudspeaker to seat A is 21 feet 2 inches. So 21.1, let's call that. To seat B is 28 feet 8 inches, so 28.65, I'll say, ish. Distance to seat C, 36 feet 6 inches, no, 38 feet 6 inches, so 38.5. That's the distance. We're professionals, so we're going to point this thing at the back row, right? We don't even have to think about that because that's what professionals do. So what would be the off-axis angle? Well, let's draw some lines here and see what we got. There, there, and there. Measure angle. Angle to the middle seat is 17 degrees. And angle to the front row is 41 degrees. There we go. Okay, loss over distance. What is 20 times the log of 38.5 divided by 28.65? 0.6? 2.6. Anyone else get that? 28.65. Okay.
Are we doing 2 decimal places, like on purpose, or just one? Doesn't matter.
Yeah. Generally, I would say 2 decimal places, but there's a margin of error there. Okay. What about to the front row? So 20 times the log of 38.5 divided by 21.1. 5.22. That's what everybody got? Okay, let's consult our polar plot now.
Also, I just realized this when we're calculating for the dB difference, we're using the where it's pointed as like our reference point.
Yeah,
Okay.
exactly. Okay, here we go. Vertical polar data, 1 kilohertz. Here's the plot. 6 dB per division looks like. So when we go 17 degrees off axis, that is about here. I'm going to say we've lost 1, maybe 2 dB. What do you think? Right here? That's going down because, yeah, to the right. Yeah, that's because, remember this is, the other one had the loudspeaker tilted so that, the 0 was over to the right. This one has it to the front, or to the top. So if the loudspeaker is pointed this direction, that's where the back row is. Which means when we go to the front row, we'll be going this way.
Yeah, they just numbered it because the last one had 330 degrees below the 0 point.
Yeah.
So there's just like no standardization.
No.
For that.
No.
Okay.
Nope. But we're looking for 17 degrees, which is about there. Which I'm going to, anybody, do we need to fight over this? 1 dB or 2 dB? All right, -1. What about 41 degrees? That's going to be about here-ish. That's maybe 3. Yeah. -3. Perfect. All right, total loss. 5.22 minus 3. 2.22. I know I could, couldn't I? 2.6 minus 1, that'd be 1.6. Perfect. So far, so good. All right? All right, let's take a look at the horizontal. This is where it gets a little gnarly. Okay. Now, we know, because I need to get my mouse. Okay, we know that we're not actually pointing it here on the center line. We know we've got 2 of these, so we're pointing them off axis, right? Well, how do we know how far off axis we're going? Well, we can just check the spec sheet here. Let's go back and look. So they're saying horizontal coverage 90 degrees between 6 dB points. So I'd be willing to bet that if you look at this bracket and measure that angle, you're probably looking at 45-degree angle horizontally. That's probably what they're looking at here, okay? So let's figure out a 45-degree angle. Let me turn that on my polar tracking. So I'm going to draw myself a line there, and I'm going to rotate it. Ooh. All right. Oop. Rotate, base point, reference be here to there. And I'm going to look for that 45 degree that I put into polar tracking. Actually, I can just type it in. 45 degrees. There we go. So 45, I go that way. I should have done -45. And then I can mirror it across here. Okay. That's where the 2 things are pointed. All right. So now what we can do is we can put some new points in. We want to stick with these rows that we're already using. So we're going to have something here. If I just go off of that middle row, it would be there. And then I'll put another one there. And I will call these D and E. All right. So this will get a little bit different now, because now we're pointing here, which means that really our on-axis is now in this spot, and we're pointed at the back row. So let's I think I'm actually going to swap these.
Is there any reason why you're not including an X on the last row?
Well, because the last row gets cut off a little bit before I hit the on-axis point.
Oh.
So I'm going to actually put B down here now. And I'm going to put A down here now, because this is now where we're on axis, okay? And this will become D, and this will become E. Oops. Okay, and then we'll worry about this later. Okay, so how far away from the loudspeaker is seat B? not entirely clear, right? Because, we were using the section view before. And the section view makes a certain amount of sense, but once you start going horizontally, it gets a little weird, right? So this is, what you're about to learn is the extent of my mastery of trigonometry. Anything beyond what I'm about to show you, you're not going to get much out of me, okay? But we can figure it out, right? Using the Pythagorean theorem, we can figure this out. And the Pythagorean theorem states that a squared plus b squared equals c squared. If a, b, and c are the different sides of an of a right triangle, right? So we could create that right triangle. So if we want to figure out b, we're really looking for a line that is here. So that line is the b side of our triangle. And that distance is what? Oh, wait, no, sorry. I'm doing this wrong. It's this. That's the side we want from the section, because that's the height, okay? So this will be one side of that triangle, and that's going to be 12 feet 7 inches. So what would we call that? 12.6 inches? All right, and this is to seat B. So I'm going to insert a couple rows here. A is 12.6. And then the B side of the triangle we would get from the ground plan.
What are you solving for right now?
I'm solving for the line we can't see, which is the line between the ears of the person sitting in that seat B and the spot where the loudspeaker is, because that spot is like over here and up, right? But all I have is ground plan view, and then I have height. But there's this diagonal line that I'm trying to find.
When you're sitting there, the speaker's like here, right? So
Yeah.
you're trying to find that?
Yeah, I'm trying to find that line. So the two lines of that triangle that I have is if I'm, like here I am, and I'm at that loudspeaker, okay? So I have the line that goes from here to directly under the loudspeaker. I have that from the ground plan. And I have the line that goes from there directly up to the loudspeaker from the section. That's the other side of that right triangle. And I'm trying to find C, which is the line between my ears and that driver. Sure. Is that what they call that?
Yes.
Okay. See, you all took way more math than I did.
And you can't just measure that in AutoCAD by drawing a line?
No, because the z-axis isn't accounted for here. We just have 2D drawings, right? We're looking for something. If this was a 3D drawing, then yeah, we could just go click, click, and we'd have it. That'd be cool, wouldn't it? A 3D button, that would be nice. Okay, so I'm just going to measure that. That's 28 feet 3 inches, so that'd be 28.5. Some of the ones that want to impress people do, but it takes a lot of time.
That sounds like a lot of
I was wondering if there's a 3D version of AutoCAD, in theory, does that work or does it still not work?
It would work.
Because people use AutoCAD for architectural.
Yeah, no, you could make a 3D drawing of DeMille in AutoCAD. You absolutely could do it. It would take you a million years, but you could do it.
No, I just mean would that be successful for what we're doing right now? Not could do, but if you were to draw that line in a 3D model space, would it actually?
Yeah, it would. And we will do that in ease, by the way. We will make 3D drawings of the space in ease. And then you do just click, click, and you got it. Okay, but remember, I'm trying to teach you the hard way first so that you appreciate the easy way.
So this is the hard way.
This is the hard way. Yes. Okay, so I got two values here. We're going to do 12.6 squared and 28.5 squared. I will sum those together, and then I will take the square root of that number, 31.16 feet. That's how far that seat is. So it's not 28.65. It is 31.16. Now, in reality, that's not a huge difference sound-wise. We're not going to get a ton of difference dB-wise there. But we at least now have the actual distance. And we can compare that from a distance point of view, dB loss over distance. We can compare that from seat, well, what would be our new seat C if it existed? It would be here. That would be seat C if it existed. Okay. Well, because it's curving, right? So the actual distance. This is the same distance that seat C was in the middle. It's just outside the wall, right? So no one's actually going to have their ears there. It's just for purposes of getting what we need. So we could figure that one out too. But again, we're about out of time, so I don't want to belabor that point too much. But here's where it becomes very helpful. Is we know that this is now on axis, right? And we know that our vertically off axis will be the same amount, right? Because we know that we are still, from an angle point of view, vertically we're still the same. We're on the same middle row. Okay, we've just moved over to the side. So it's the same vertical angle, which means we have the same off-axis angle and the same directivity loss. We just need to figure out the dB difference loss. We'll assume it's pretty close because we didn't change that number dramatically. Okay, it's not going to be too. It was a little bit farther away, so it might be like 2.7 or something dB, but it's not going to be hugely different. So total loss there is going to be fine. But here's where here's the concept I want to drive home. Okay. Now let's figure out this seat here with our new angle horizontal. Okay, so we are now measure geometry, angle. We are now 45 degrees off axis horizontally to seat E. What did it say? 45. 45 degrees. Okay, now we know if we look at the horizontal polar plot, 45 degrees is, oh, gee whiz, look, 6 dB down. Right? See that? So directivity loss, -6. The difference in distance, well, we know that. That was we can get that straight off the section, which was, I deleted it. Let's measure it again real quick. Measure geometry from here to there, 28 feet 8 inches. So that's going to be, what did we say that was? 28.65-ish. Okay. So what is 28.65 compared to 38.5? So that'd be 20 times the log of 38.5. Well, yes. 20 times log of 38.5 divided by 28.65. 2.6? 2.56 dB. Oh, you got? So we have vertical, now we're talking about vertical directivity loss or horizontal directivity loss is -6, but we have a vertical, I'm going to need to insert a new row here. So this, we have horizontal loss, and that's actually the -6 because we were horizontal. And vertical, we still have the -1. Now in reality, if you could get a 3D plot of this, it would be not necessarily the sum, but that's the only information we have. So we know we lose 1 dB going off axis vertically, and we know we lose 6 dB going off axis horizontally to that spot. right? Because this spot, if I go back to, if I go back to the ground plan, remember, the loudspeaker is pointed here. And so at this spot, we have gone off axis vertically because we've come down, but we've also gone off axis horizontally because we've moved from here to there. So we're going off axis two ways. And we don't have polar plots that show us that particular slice. So we just have to assume that we'll just sum those two things together. In reality, it's never quite that much. It's usually a little bit less than the sum of the vertical and the horizontal loss. But if this is all you got to work with, you just use that, okay? So we are, total loss is -7 and 2.56, so -5.56 comparatively speaking. But we also know that eventually we're going to have a copy of this thing over on the other side, and it's also going to have a 6 dB down point here at that middle. And so we will overcome that horizontal loss. That will sum to 0. So we know if there's only one, we have -6. But if we line up the two -6s, this becomes 0. And now we are actually 1.56 louder.
Would that still be an acceptable loss because it's under
Yeah,
-6?
totally. All right.
I have a question.
Yes.
How do you take into account the curvature of the back wall mathematically? Because that affects how it sounds in space.
That would involve reflections, which we'll learn about in a few weeks. So you absolutely have to think about that. But for purposes of this problem right now, pretend that that's not a problem.
Pretending that it's just a straight wall.
Pretend that there is no wall
Okay.
for purposes of what we're doing right now, right? We're not worrying about reflections yet, okay? Now, let me show you what I'm going to ask you to do. I've now shown you all the little steps, okay? Just a little I've given you the nuggets of information you need to pull this off. Let me show you now what you have to do. So if you are not Jaden, this is your assignment. So your assignment is to use published directivity data, such as polar plots or isobars or whatever, and I've got a link in the modules for some PDFs of different loudspeakers, to determine an appropriate center cluster for the Patron's Theater using the attached CAD drawing. So I have a CAD drawing that you will download that's already set up, ready to go for you. So let's download that and take a look at what it is. There it is. And there's the seats. So you're looking for, how do I cover those seats? With one loudspeaker, ideally. Okay. Now, here is the specs. I want you to do this for 2 kilohertz instead of 1 kilohertz. And I want you on the CAD file to show me on the ground plan and section view which seats you measured, right? So show me where your points were. What seats did you measure? And I want you to do 2 different ones. Okay, so pick 2 different loudspeakers and figure out those seats and tell me how loud it will be at each of those seats. Okay? And then based on what you find from those 2 different loudspeakers, tell me which one you think covers the most evenly. Which one has the least amount of variance from seat to seat based on that directivity and loss over distance equation. Okay? So which one covers most evenly? And just do a little piece of paper, type a little paragraph up that says, along with your data, so you're going to turn in the CAD file that has the labels. I would suggest turning in some sort of spreadsheet like I just did that shows all of that work you did, so I can see, because you'll probably mess some things up here and there, and it's helpful if I can see where you went wrong. Like, oh, look, you used the wrong number here or whatever. So just do that. And then a little piece of paper that has a paragraph that says, I've analyzed my own data, and my own data says that this loudspeaker covers more evenly because there was a difference of 3 dB from seat to seat. Okay? That's what we're looking for. Now, I want to temper expectations here a little bit. I'm not expecting that any of these will be amazing. Okay? This is kind of a hairy thing. There's a lot of details you got to wrap your head around here. I want to see you try. I want to see if you can wrap your head around this concept between what happens when you take inverse square law and loudspeaker directivity and merge them together. Can you understand that concept and see what happens? If some of your points are wrong or it's fine. I just want to see you try to merge those two concepts together. Okay? So my expectations are not super high here, but I do want to see you try to hit this standard that I've written this paragraph. Okay? If you are a Jaden,
I'm scared.
you have to do something slightly different.
Maybe like do it for line arrays.
No. You have to do the same thing. So it's but you're just doing a different theater. You're going to do Friedman theater. Okay? Now, the reason Friedman theater is a little more complicated,
It's a big theater.
it's bigger for sure, but the audience is actually spread out over a much wider area. Okay? So, everyone else is probably going to be able to pull this off with one loudspeaker. Okay? Because it's a small theater, little seating area. They're going to be able to find one loudspeaker that they hang on a pipe somewhere it can cover and it'll be fine. You, on the other hand, are going to have a little bit tougher challenge because you've got a much wider area here. You are probably going to have more than one loudspeaker to make this happen. So you're probably, I'm going to give you a couple of tips here. Okay? You are probably looking for one of two solutions. Either you are looking for something here-ish that has two cabinets, one pointed here, one pointed here, arrayed on 6 dB down points, just like we did in DeMille. Or you might be looking for something where, is it possible for me to get a different color? I don't know if this will work, but you might be looking for something that would be like here, here, and here. 1, 2, 3. Get it a little closer, and then it'll be narrower, and you cover each seating area like it's separate. Either solution is doable, and either solution will work. Just depends on which one you want to pursue. Okay? So, but other than that, same thing. Show me two different solutions. Turn in your work. Write me a written recommendation of what you think works best. Now, when is this due? I believe it's due Friday. Okay? So on Friday, we'll look at it. We'll see how you did. This is where the real learning will take place. I've given you the very quick crash course with a little bit of information. I want to see you try to apply it, and we'll see what everybody does, and we'll spend Friday looking at everyone's ideas, and we'll start connecting some more dots. Okay? That make sense?
Mm-hmm.
Yes, Courtney.
When do we decide, like, the way the loudspeaker should hang? Like how this
Yeah, like where do you want to put it and everything?
sideways? Like, 'cause I've never been vertical and horizontal, just like
Yeah.
directivity, but like why is that sideways?
Well, that's a subwoofer.
Okay.
So it's a different thing. But if sometimes horns are asymmetrical, meaning like that first one we looked at said 60 by 60. They're not always 60 by 60. Sometimes they'll be 90 by 40 or something like that. And so you might decide, well, I want the 40 on the vertical and the 90 on the horizontal. And so I'm either going to rotate the horn or I'm just going to rotate the whole box to get the coverage, the wide coverage where I want it and the vertical coverage where I want it. Just depends on the scenario, what you're looking for. And a lot of loudspeakers now, that's becoming very popular. Most loudspeakers that are worth anything, you're going to be able to take that horn and go and rotate it, right?
For this assignment, would it be smarter for us to just pick a loudspeaker and work with that, or figure out the angles first and then choose the loudspeaker?
Yeah, that's a good question. So I don't really care. At this point, I don't so much care whether your idea was good or not, or right or not, or wrong or not. I don't really care about that. I just want to see you pick a couple things, interpret the data about them, and map it into this space, okay? Whether it's good or bad, it doesn't really matter at this point. But if you want to try to achieve good, then yeah, you might start by saying, well, what is the actual problem I'm trying to solve? What is the area I'm trying to do? And then try to look in that list of things I gave you for something that fits the bill. If you want to take that extra step, that's fine. But I'm not super concerned about that yet. We will get to that part later when I teach you ease. What I really want you to do is just pick something, anything at all from that folder I gave you, or go download something of your own and see if you can figure out approximately what it will do if you hang it on a pipe and point it at that audience, right?
You said the list is in modules?
Yep. So if you go to the modules, you will see polarplots.zip. That has a whole bunch of PDFs with polar plots in it that you can use.
I have a question.
Yes?
Can we just like put the speaker anywhere? Do you want us to take into account like where buttons are? Or like do we have to think about
Put it wherever you want.
Also,
any place?
do the polar plots not come in the manuals of the loudspeaker?
Usually they do. Yeah.
These are just like basic ones?
Yeah, these are ones that I found that I like,
Okay.
that are interesting. If you want to go find your own, that's fine.
Because if the loudspeaker that we choose, the frequencies will be different
Yeah.
on those polar plots.
Yeah. Yep. Okay. All right, we got to go because next class is coming in. But if any of you have any other questions you want to say and ask, that's fine.
I do.
Let me stop my recording, if that's possible.